So if you've been paying attention, okay, we believe, and scientists believe for a very good reason, that the universe emerged from a big fiery explosion that was called by, I think his name was Arthur Hoyle, was called the Big Bang, to discredit it, right? And the only reason we think this is that we see, when we look away from Earth and back in time, we actually see a big fiery wall. And the only reason we think this is that that fiery wall has exactly the radiation that a fiery wall should have. And the only reason we think this is that that fiery wall has minuscule quantum fluctuations that are exactly what the Heisenberg uncertainty principle would predict for something that had been once small and part of quantum mechanics, but is now big. Okay, the only reason we think this is that the universe is now expanding at a rate exactly predicted by the fiery wall and the explosion. Yes? Okay. And the only reason we think this is that the elemental abundance, if we look away from stars, okay, if we look away from stars in the universe, the elemental abundance is exactly what it should be if there was a fiery, dense beginning that could create things. And this is where I believe we left off. You guys were on the edge of your seat and you're like, and then we had to cut away. Okay? But a big fiery explosion created elements, and it created 1/4 helium, 3/4 hydrogen, because those are the species that could exist, and probability just says it's going to land in one of those 4 places, right? So that's all the supporting evidence, and that's pretty good, and there really is no other show in town. Nobody's got some other theory that might someday... Can we stop? Whatever this little conversation's going on. Okay? There's no theory that's going to come along and say, oh, no, it didn't emerge from a singularity, it's on the back of a turtle or something like this. I mean, I don't know what it would be, right? But nothing like that's going to come along. But there are some holes that we haven't filled, in the Big Bang. And so that's what we're talking about today. Well, there is Chris Murrayism, but we'll get to that, right? That's one of the competing theories, other theories, right? So basically, let's just look at scenarios here. There are some paradoxes with the Big Bang, but it's what happened, so we'll have to get over those somehow, right? This is, you can graph the universe. This vertical axis is size, this is time, so time's going on. And sometime later in time, yeah, he's here. Okay, sometimes later in time, there are 3 possible scenarios. One is that the universe is never going to stop expanding. Okay, this we talk about negative curvature as well. We also talk about less than critical density. In other words, it doesn't have enough density. There's not enough matter there so that gravity's strong enough to bring it back. And this is pretty conventional thought. There's something else going on that we'll talk about in a sec. But there it is. All of these things have gravity slowing the universe's expansion down, as well it should. Okay?
We're going to travel all the rest of
if it's
by 2012.
Yeah, well, I don't know where 2012 is on here, right? Or something like that. Right. But anyway, no, this is like now, right? So now there's, the other possibility is that if we have positive curvature, that means we have enough mass to actually curve, and we can't picture this, but we're curving all of the universe into a big ball, but it's a 4-dimensional ball, so it's like the globe, like this, right? So it's got positive curvature, it's got more than critical density, it's got enough mass, and this is what we can really think about, right? That it's actually going to come back and there's going to be another Big Bang. It's going to make a singularity. It's going to explode. It's like, it keeps exploding. I hate that, right? Okay. And then it could be that the universe has exactly the right velocity, has exactly escape velocity. It's going to fly apart. And as time approaches infinity, this thing approaches level, even though it looks pretty level right here. Okay. That's the notion. Okay. And so... Yeah, at infinite time, the velocity will reach 0. But before that, it's just approaching 0, right? I'm going to pass that back. Don't read it, though. It's like a personal note. Okay? So 3 possible scenarios. Blah, blah, blah. Right? Okay? Now, here's a little tricky thing, right? As far as we can tell, looking at really, really far distance indicators, these are type 2 or type 1a supernovas, these ones that collapse because they when they collapse to a white dwarf, right? When they collapse to a white dwarf, they don't quite have enough mass to do that final collapse in supernova, but somebody keeps feeding them food. Like, here, eat, kind of like our dog. right, this fall. I kept feeding it food and the dog kept getting bigger and bigger, right? And it subtly approaches the Chandrasekhar limit and then explodes from that limit, has exactly pretty much the same brightness, right? So these are sort of standard candles and they're super bright. And so the type 1a supernovas have given us evidence that actually the rate of the universe expansion has increased. Now, the only force we know that works at galactic distances is gravity. This means there's another force and we don't know what it is. And this is sort of bad, kind of makes us look bad. Doesn't that look bad? Yeah, go for it, right? And so really basically a scientist's initial reaction to anything like that just basically trashes all these paradigms, right, is that we've got to discredit the data. Because that's all you can do, really. You can prove something wrong. You say, oh, that set of data wasn't valid, right? Okay. Everybody's tried, nobody's done. In fact, pretty much the general consensus now is that, yeah, it's expanding. We don't know why. It could have to do with the next topic we're going to talk about, is that there's a lot of the universe we don't even know what it is, right? So there's probably something that at a certain density, right, it's actually causing, because it's so far apart, gravity's not strong, and this, whatever this other force is stronger. It could be a dark energy sort of thing, right? Yeah, there we go. Now, we also talk about curvatures, and we'll talk about this in greater length, but this one is negative curvature. It's less than critical density. And so, I mean, it's hard to picture a two-dimensional shape that's negatively curved. A three-dimensional, forget it, right? A flat, though, this is good, right? Flat is flat. We can understand flat, right? Euclidean geometry works in our space. And then the final one is that it could be positively curved, right? So these are the densities. So I think we talk about curvature next, right? So let's go back to 2 dimensions. We can think about 2 dimensions, right? If it's flat, if a surface is flat, one of the ways you can measure its flatness is you can draw a circle, measure its radius, and if the circumference equals 2 pi r, it's flat. Euclidean geometry is flat, right? Interior triangles have interior angles that add up to 180 degrees, and again, that's evidence of flatness, right? But if we have a 2-dimensional surface, the rule for if it's got positive curvature, the circumference actually less than 2 pi r. I mean, look at that radius. Because of the curvature of space, that radius is exaggerated, correct? Because it went up, right? So it's longer than it would be if space were flat. So therefore, the circumference is less than 2 pi r. That's weird, isn't it? Yeah. So if you go into space, if we could draw a big circle here in space, big enough, right, and we could do that comparison, if the circumference is less than 2 pi r, then we have positive curvature, right? Triangles, though, if we draw them, have more than 180 degrees. And of course, famously, we had the example, right? If you just make right-hand turns, drive along the equator a long ways, right? Exactly what this length is, a quarter of a circumference around, right? Take a right-hand turn, go all the way up to the North Pole, right? Take another right-hand turn, go all the way down. You've now made a triangle with 270 interior degrees of angle. But why stop there? Why not just drive like nearly halfway around, then go up? Don't turn right, just turn like 20 degrees off. Yeah, that's like a lot of angle, isn't it? Yeah, sky's the limit once you get to 270. It's like there was some sports star that was quoted as saying, I'm out there on the basketball court giving 110%, and you just can't give more than that. Mm-hmm. Well, if you think about it, if you're giving 110%, why can't you give 120%, right? Once you start hyperbole, where's the end of hyperbole, right? I don't remember who that was. I can't remember who that was, but that's kind of funny. It's like mine goes to 11.
It's like Dennis Rodman.
Yeah, it might have been, Okay, now, that's from Spinal Tap. Haven't you seen Spinal Tap? Oh, you've got to see Spinal Tap. It's funny. This is Spinal Tap is the name of the title. If you look Spinal Tap, you'll also probably see it. If you have a shape, a saddle is a shape that has negative curvature. This is a 2-dimensional shape. There are other shapes, okay? On a saddle, the circumference is actually more than 2 pi r. Triangles have actually less than 180 degrees. And here's a saddle shape. I was like, I've got to make a saddle, so I cut a piece of pipe like this, and then I put plastic on there and held it over a Bunsen burner, and it shrunk, and there it is. Don't be like whatever these kids are. They're like, oh, I'm going to poke my finger into the negative curvature. No, no, no. There it is. Just kind of like, oh, look at that, right? Okay. If you think about a saddle, if you think about that surface, okay, if you draw a circle on that saddle, doesn't the circle go up and down? So therefore, the circumference is actually greater than 2 pi r because it spends time going up and down, whereas a flat circle is just 2 pi r. is equal to the circumference, right? And so, so this is a negatively